Welcome to part 1 of our video about area from a calculus perspective. In this video, we will not actually delve into area just yet, but rather learn the building blocks to finding the area underneath a curve, the fundamental theorem of calculus, and integration. In order to get there, we need to understand sigma notation. This Greek letter right here is the uppercase sigma, and we use it when we need to take a sum of multiple or an infinite amount of terms. This is sometimes also called a summation tool because it is used to find a sum. Here is how we use it and the notation used with it. The sum of n terms, called a sub 1, a sub 2, a sub 3, telling us which term it is, so a sub 1 is the first term and so on, all the way to a sub n, the nth term. We write that as sigma, or the sum, from I equals 1 to n of a sub I. This just means that we basically have a function in here telling us what we're doing. The I is just a dummy variable. It doesn't matter what variable we use, but most commonly we see I, j, and k in calculus. And this lower number tells us the first value to plug in for I, and this upper number up here tells us the last value to plug in. We want to plug in every single integer in between. I is called the index of summation, which is a nicer way of saying the dummy variable. A sub I represents the ith term, so a sub 1 represents the first term, and so on. Then the upper and lower bounds of summation are, this is the lower bound down here where we begin plugging in, and this is the upper bound up here. Most commonly, we begin at 0 or 1, and the upper bound, it just depends on what it is. Sometimes it is n. Let's take a look at an example down here. This is telling us that we want to take the sum of I squared, beginning when I is 1 and ending when I is 4. So we need to plug in 1, 2, 3, and 4 into here, and then add up those 4 terms. The first term we'll find is a sub 1, which is plugging in 1. We plug in 1 to this function right here. So we're plugging in 1 for I, so we'll have 1 squared. This is our first term. Our second term is going to be plugging in the next number, the next integer, which is 2. So we'll have 2 squared, then we'll plug in our next number, and finally our final number, 4. We know that we stop at 4 because that is our upper bound of summation. Adding these together, we'll have 1 plus 4 plus 9 plus 16, and so our final answer is 30. Obviously, I started with a pretty simple example, but that is the general idea of what we need to do. Let's take a look at a few more examples. In number 2, we want to take the sum of I from when I is 1 until I is 7. So that means we are going to be starting by plugging in 1 for this function inside here, which is just I. So we'll have 1, and then we'll go all the way up to 7. Now I'm going to write this like this. We're keeping a pattern. And to add all those together, our answer is 28 when we add them all together. In problem number 3, we want to take the sum, starting at 3 this time, and ending at 5. So we only have 3 terms, plugging in 3, 4, and 5 into this function right here, I squared over 2. So we'll have 3 squared over 2 plus 4 squared over 2 plus 5 squared over 2. When we do the math on this, we'll end up actually with 25. This next example looks a little bit more complicated, but that's really only because we don't have a numerical value in for n, and n is also a part of this inside function here. But either way, we're going to approach this in the same way. There is not really a place to stop, per se, so we are going to do a sort of mathematical maneuvering here, but we do know where to start. We need to start by plugging in 1 for I. So our first term is going to look like this, 1 over n, and then plugging in 1 for I. So we'll have 1 squared plus 1. I'm not going to simplify it at all. That is sufficient. Then our next term is plugging in 2. Then our third term would be plugging in 3, and so forth. However, we do not really have a place to stop, so I'm going to just do dot, 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 and then our final term is when we plug in n, whatever n may be. So I'm just going to plug in n everywhere there's an I for our final term, and there we go. Now, did we actually find the sum? I mean, we didn't actually find a numerical value like we did in numbers 2 and 3, but that's because we were not provided an upper bound of summation that was a numerical value like we were in numbers 2 and 3. So in this case, we sort of provided ourselves a sum formula, if you will. Whatever n happens to be, we can plug it in and then find the exact sum for that specific value of n. Sometimes evaluating certain summations can be challenging or just downright monotonous. So we have a few properties and some common summation formulas to help us out. So I highly recommend that you write these down. So go ahead and pause your screen to get these written down, and then we can delve into how to use them. Part A certainly looks monotonous. Not exactly challenging, but just kind of like it would take a long time. We need to sum 25 terms, multiplying them all by 152. It seems like there could be kind of a shortcut to this. Well, what we can do is first use this property up here that says we can bring that constant of 152 out front and then just evaluate the summation. So let's bring that 152 out front. So we're left with this right here. Now what we can do is evaluate the summation by adding the numbers 1 through 25 together. Now, you can definitely type this into your calculator pretty quickly, but there's chance for error and it just might take a while. We can use this special formula for when we're summing the values from 1 to n of just those values, I. What this says we need to do is we need to take n, multiply it by n plus 1, and then divide by 2. This is a really, really cool idea, and there's a great proof of it. Gauss came up with this, and it's an awesome proof if you ever want to look into why summing the numbers from 1 through n is n times n plus 1 over 2. When we actually figure out what this is for 25 being n, we take 25 and multiply it by 26 and then divide by 2. So using this formula, we still, of course, have the 152 out in front. Then I'm taking care of this part here and using our summation formula number 2, taking 25 times 25 plus 1, and then dividing by 2. In your calculator, if you want to do this a little bit simpler, 26 over 2 is really just 13. So we're taking 25 times 13 and then multiplying it by 152. When we do all that multiplication, we'll get 49,400. So while not a super challenging task to evaluate this original sum, we can use the property of bringing that coefficient out front, and then we can also use this common summation formula in order to make it a little bit simpler. Now part B looks definitely crazier and more challenging, and also we have an upper bound of summation that is not a numerical value. In this case, it's just n. Now, this is something that we will see quite often in the short future when we are working with summation notation with limits as n approaches infinity. And so I wanted to just include this as one of our examples here. Now, what we can do is actually utilize the second property of summation because we do have a sum, or in this case, a difference. So we can just break it up into two separate summations. All right, so now take a look what I did. For breaking up this first summation here, I actually moved the 152 out front. We've already discussed why we could do that because of this first property. Here in the second one, of course, there's a minus sign connecting them because there wasn't here. I simply wrote out what I over 2 quantity squared is. It's I squared over 4. So I just simplified that a little bit. The reason that I did that is because we actually do have a k value again. And just like we had in 152, that we can bring out front of the summation. Can you see what that value is in front of the I squared? It's 1/4. Now I've rewritten this second term with the 1/4 out in front. Now if you take a look, we have the summation of I equals 1 to n of simply I. We dealt with that already, except in the previous example in part A, n was 25. In this case, n is just n. So what we can do is actually use that again to replace literally this up here. So I'm replacing this guy with n times n plus 1 all over 2. Then we can do the same thing for our next term because of what I squared is defined as, or rather the sum from 1 to n of I squared. It has this first part, yes, and it also has 2n plus 1, and it's all over 6. This is another cool proof if you are interested in seeing why this is. So I've replaced each summation with what it equals using 2 of the common summation formulas. Now in this problem I'm going to stop here because we haven't been given further direction. However, as I mentioned previously, very shortly we will be finding the limit as n goes to infinity, and it's important to be able to get everything in terms of n rather than I when we have summations that go from 1 to n. Here we want to evaluate this summation for n is 10, 100, 1000, and so on. We actually want to see what happens as n approaches infinity. Now, in order to do this, the best course of action is to simplify this using n, and so we have a nice simplified version that we can then plug all the values of n into, rather than trying to evaluate it separate times by plugging in 10 here and then going through the process and so on. So let's simplify our summation here as best we can. We actually can see that we can rewrite this summation as 1 over n squared times I minus 1. Now the reason that I did that is because we can see that this is a coefficient and it can actually be moved out front by that first property that we've learned. So we can simply rewrite this as 1 over n squared and then times the summation from 1 to n of I minus 1. Now we can use the next property because we actually have the summation of a difference, so we can actually write that as the difference of the two summations. Here we can see that I split up the sum or the summation of this difference into the difference of the two summations. So we can split it up using that second property of summations. Of course, I needed to keep it in parentheses because this 1 over n squared is actually multiplied by this whole thing, so it's multiplied by both terms. I've added in here these common summation formulas because we see that we have actually 2 of them right here. We have one that we've utilized previously, the sum from 1 to n of I, and that is equal to n times n plus 1 all over 2. Then one that we haven't used yet, which is the sum of 1 to n of a constant c. In this case, our constant is 1, and so therefore it's equal to 1 times n, or just n. So let's replace both of these with what they are equal to according to their formulas. Once we've done this, we can simplify even more within this parentheses. So what I have done in this next step is multiplied n times n plus 1, then kept it over 2, but got a common denominator of 2, so I had to multiply n by 2 over 2 in order to have that common denominator. So we can write it all over 2. Next, we can combine some like terms. Next, we can simply multiply straight across. There are a few different ways to simplify this. We can see here that all 3 terms can be divided by n, so they can all be simplified and be divided by n, so we'll have n minus 1 all over 2n. So n minus 1 all over 2n is the general way in order to evaluate this original summation up here. Now we can plug in any n value that we want, specifically 10, 100, and 1000. Organizing our solutions in a table provides us this. We did find, using algebra and simplification techniques for summations here, we found that this summation actually simplifies to n minus 1 over 2n. We were then asked to plug in different values of n to see what happens as n approaches positive infinity. When we plug in these 3 values of n, we get the following outputs. Then if we plug in 10,000, we do see a pattern here, and it is true that we'll get 0.49995. We can clearly see that as n is getting larger and larger, approaching positive infinity, that our summation values are approaching 0.5. We come to the conclusion that the limit as n approaches infinity of this summation here from I equals 1 to n of I minus 1 over n squared actually equals 1/2. Now, we did find this using a table and using a lot of simplification, but when we look to what this ended up equaling, n minus 1 over 2n, if we find the limit as n goes to infinity, we can clearly see that our leading coefficients in both the numerator and the denominator simplify to 1/2. Therefore, that is how we get this final answer of 1/2. In part 2 of area from a calculus perspective, we will be using these ideas of the limit as n goes to infinity in order to find the area under a curve.